So apologies for the grammar and the weird spelling, but we're going to talk about how big we think the universe is and how much bigger it's getting. The universe is vast and getting even vaster. I wanted to avoid something like vaster. From our observations using spectroscopic analysis and taking into account the Doppler shift, the reddening of things, currently it's believed that the observable size of the universe is about 28 billion light years. That's the B for billion and LY for light years. That's us using medium infrared imaging aboard things like the James Webb Space Telescope, and also the microwave radio reception that we've done, a number of instruments that we put up into Earth orbit and L2. It presumes that there's an expansion, and that expansion is an acceleration, not a static velocity, and that it's a constant, and that the expansion is sourced from dark energy. We don't know exactly what it is, so we call it dark. It has nothing to do with being black. It is just, we don't know what it is, so we call it dark. If we take into account the acceleration, so we see something and we know how far away it was based upon the light shift when we saw it, and then we judge that amount of time for the travel at light speed plus the acceleration. And so we can now make a guess as to how large the most distant things are in the universe. And it turns out that's called the co-moving size, about 94 billion light years. This is not the universe that we can see. This is the things that we have seen. And since the light left them that we did see, how far has it moved since then? So expansion, 94 billion light years. But we're not sure that that's as far as it goes. It may go a lot farther because there is light that hasn't reached us yet. Kind of makes sense. Wait a little while, we'll see even further away things. But maybe we're just not looking shifted enough, and there are things that are out there that we're just not currently looking at. So we know that the Doppler shift will take you from visible to red to medium infrared to far infrared, or FIR, and the James Webb Space Telescope cannot see in far infrared. It can see orange, red, near infrared, and medium infrared, but it can't see to far infrared. So there's a gap there that we have no instrument to observe. And then if you go even farther shifted out, you get into radio, but it's not the highest frequency radio, it's microwave. So it's not the highest frequency radio, it's down into the shorter wavelengths of radio, microwave. And that's the ALMA array in South America. But there are further shifted radio frequencies that we could look at, but we don't have anything that's up there looking at it. There's, ultra high frequency, very high frequency, and short wave. Not all of that penetrates the Earth's atmosphere, but if we have a probe in space orbiting the Earth or out at L2, maybe we could see in those other frequencies, but it'd have to be fairly large antennas or arrays. But if you go down even further in reddening or increasing the wavelength, there's also very low frequency and ultra low frequency. And we have no instruments in space for that. But there's also theoretical frequencies below ultra low frequency, extremely low frequency. It's not its official name, but XLF. But we have no instrument technology to observe that. And so they just say, well, that stuff doesn't propagate well through the open universe, and therefore we're not going to go to the effort to make any technology to build it. But I'm not quite sure that's accurate. I think it's just convenient. But it presumes that the universe expands at a constant acceleration. The exact number of that expansion, the Hubble constant, is currently under dispute between radio astronomy and infrared astronomy, and that's referred to as the Hubble tension. We have information that says maybe the Hubble constant was a different value in the early days of the universe versus today, which means that the constant is not really a constant. It's a different physics measure called a jerk or a jolt, but commonly referred to as a jerk. That's a variation in acceleration. Now, from what we've seen so far, the universe is flat. That doesn't mean that it's like a sheet of paper. That's just a visual representation. What it means is it's uniform. So as we go over a distance, the density of the material and how fast it's moving is uniform. But they like to refer to that as flat. and it confuses a lot of people. But there's a parameter called omega. And if omega is less than 1, you get a certain curvature, more spherical. If omega is greater than 1, you get a different curvature. You get a hyperbola, which is sort of saddle shaped. And if it's right in the middle, if it's precisely 1, then you get flat. But it's actually a sphere. It's just uniform throughout the sphere. And they were doing the presumption of it being flat and not curved based upon observations from the Gaia space probe. Gaia was looking in this galaxy, so we don't know the expansion as it applies to other galaxies. As the Rubin Space Telescope in South America starts going online, they'll start observing other galaxies for how fast they're moving away. And if we see farther and farther ones moving away at a different acceleration, then sorry, Hubble's not a constant. Hubble's a jerk. So what exactly is getting bigger? Everything all at once, but not everything. The distance from the Earth to the most distant thing that we see, yes, that's getting to be a bigger number. And we're evaluating that based upon medium infrared redshift of galaxies. But it makes the presumption that all those galaxies out there have identical star color populations to the Milky Way. Because when you're judging the particular color of a galaxy, you're not evaluating the individual stars, you're evaluating the bulk of the brightness from all the stars in the galaxy that are facing your direction. So it's a blending of the colors, and you look at the shift to find out what kinds of metals are in the spectroscopic bands, and then you see how far redshifted they are, and that gives you an idea of how far away it is moving at the moment. If the presumption of star color is not correct, then if they're redder or bluer than the Milky Way is, then this presumption of constant acceleration doesn't work anymore. Sometimes it's good to listen to what they say, but don't forget to ask questions like, what if they're not all the same? Some of the stuff that you see on Dr. Becky is good at, like, here's the presumptions we're making. Like, all the galaxies out there have identical star color populations to the Milky Way. And if they don't, well, she doesn't get into if they don't, because it's an anchor presumption. If the presumption is not accurate, a lot of the conclusions they come to aren't as well founded. People like to know they have a good beat on things. So the size of the Milky Way and its age, about 100,000 light years. Well, we used to think it was smaller. And as we had things like Gaia and we could see farther out, we noticed, oh, look, there's stuff stuck on the outside of the galaxy. So the galaxy is essentially bigger. The age is based upon the spectroscopic shift of the most distant stars that we see in the galaxy that are redshifted, and roughly 13 billion years. If the universe is 14 plus billion and Milky Way is 13 billion, then there's not many hundreds of millions of years difference between the two, which says the Milky Way had to form really early on, but we don't know about that. We just know what observations we've seen. We're talking about the distance between galaxies expanding. Is it the fabric of space-time that's actually expanding, or is it just the distance between material objects in the universe? Well, let's think about that for a moment and say, if the distance between electrons and the nucleus of an atom were expanding, that would mean that it would have to have more energy to hold things together. We've measured down to quarks as the smallest thing we've indirectly measured as 10 to the minus 19th meters. This is well above the theoretical smallest thing, which is the Planck length at 10 to the minus 35 meters. We just don't have any instruments, any means of indirectly or directly measuring things smaller than that. But let's say if atoms were expanding, we know the distance from orbitals of electrons to the nucleus, and we don't see that those are changing. So is it space that's expanding, or is it that the objects in space are moving farther apart? And we're hoping that it's the objects are moving farther apart because we have no evidence that it's actually the fabric of space that's expanding. But in which direction? In all directions. There's this mapping that they show you that, we're not at the center of the universe in our galaxy, and we're not at the center of our galaxy with our sun, and the Earth is not in the center of the solar system, and therefore we're not that significant to the size of our galaxy or the size of the universe. However, the folks that did the cosmic microwave background analysis saw that there was what they refer to as phase nodal measurements. So if you take the radio frequencies of the CMB and you pick only a certain phase in this direction, and then you pick only a certain phase in this direction, what you wind up with is this line going through it that's essentially where the two phases are nulling each other to a certain degree. And that line happens to line up with the plane of our solar system. And a lot of people will say, that's curious. What does the plane of our solar system have to do with the alignment of the universe? And it doesn't. I think it's just a observation artifact. If you remember the early CMB images, they actually had the sort of flaming line that went through the center of it. And they found out, oops, that's just the midline of our galaxy. And they went in and they subtracted that out. And now you had the sort of ellipse-shaped CMB map minus that. So I think they need to do the same thing with the nodal line for the plane of the solar system. So when you talk about the speed of light, there's a propagation delay. So if something's moving at the speed of light, like the light coming from some distant object to Earth, it takes time for it to get here from wherever it is to where we are. So that's what we observe. And then there's the distance that we can tell from what we're observing. And then we take that into account and we can calculate where it might be now. And that's the co-moving distance. And there are more things out there that we haven't seen yet because their light hasn't reached us. But then as the universe expands, there are also things that we may not see, or we may see them, but as they move out farther, they may get to the point where they're moving away fast enough that, not quite the speed of light, but fast enough, it'll take longer and longer for that light to catch up with us. And if you're wondering about the Hubble tension and the difference, it's measured in kilometers per second per megaparsec. What is that unit of measure? A parsec is the parallax of 1 second, but really you can measure it in light years. So a parsec is about 2.26 light years. Well, how far is that in miles? It's about 13.29 trillion miles. So if we're measuring it in megaparsecs, that would be about 2.26 million light years. How many is that per billion light years? That's 0.00226 billionths of a light year. So it's not expanding at the speed of light. So if things are billions of light years away, you can think of it as additive of how far away it is now based upon the distance we think it is. And there's two different values you can use. There's the 67 to 68, which is what is observed in microwaves. And then in medium infrared, it's a different number. It's 70 to 74. Close. And when you're talking about kilometers per second per millions of parsecs, the difference between 67 and 74 over that vast distance isn't very much noise. But if you look at it in a very short distance, let's say 1 parsec, that's a considerable difference. So the 3 to 6 kilometers per second per megaparsec, over the overall of the universe is not much, but over a short enough distance to determine where something is, that's the crisis in cosmology, also referred to as the Hubble tension. The expansion of the universe is far less than the speed of light. And remember, the speed of light is a speed, it's not a velocity. The units of measure going from speed to velocity is just speed in a direction. So that's the only difference between speed and velocity is, when you're driving your car, you're steering the steering wheel, you know what direction you're going, how fast are you going? You just need to know your speed. But if you're out in space and you're moving at a certain speed, where are you going? Because relative to where you came from, you could be moving at an angle that says you're not really getting that much farther away, you're just getting farther out. Kind of like the Artemis rocket when it bends over and it's moving with the curvature of the Earth to gain speed. It's not going very high very fast, but it's getting faster and faster. So its speed is increasing and its velocity is changing, but it's not gaining much altitude. And then there's an acceleration, which is just essentially a change in velocity over time. So if the universe is expanding, what is it expanding into, and how long will it be doing that? It's commonly presumed that the universe is expanding. But is it the distance between objects, or is it the space itself that's expanding? If you've ever heard the discussions about relativistic measurements of acceleration, where if you're on Earth, you can feel gravity. If you're out in space and you're accelerating at 1g, you can't tell that it's not gravity. Same sort of thing. If you're on Earth and you're measuring something moving away, you don't know if the space is expanding or if the thing is moving away. Space itself has no anchor point. Now, we can't put a point in space-time and then see how far something's moving away from it at what speed. We can only judge it based upon where you are versus where it is. Now, we can put stuff out in space like at Earth orbit or L2, but they're still relative to Earth's position in space. From what we can tell, everything's expanding at an acceleration in all directions. Recent observations say the farther we look out towards the edge of the observable universe, that acceleration may not be the same, or it was different early on, and now it's pretty much the same for the last few billion years. But if we observe the distance between particles in atomic nucleus, they don't seem to be expanding. But how would we know? Because we'd need some way of measuring that to a high enough accuracy to know that. If it were expanding, we'd need some energy from somewhere to increase the cohesion of electrons versus protons and neutrons. So let's say that it's just things are moving outward. It's not really that the universe is expanding. Things are just moving outward. Into what? There doesn't seem to be anything out there that we can see. And we know that there's more to the universe beyond what we can currently see. So we just assume that out beyond that, it's just a true vacuum, a final true vacuum, the void. Is it that, or is it that the acceleration is merely dispersion, dark energy that's sort of expanding the universe? Is that really a force pushing out, or is that space that's evacuated and pulling things out? But we don't know because we have no point of reference, and we don't know how far it extends, so we don't know what the vacuum pull pressure would be, and we don't know where there is an outer shell if there is one. And the other interesting question is, if at the edge of material, at the edge of the most distant objects that we can't see yet, if they're moving out, is that they're at an edge and the edge is moving out, or the edge is already out there and they're just trying to seek an edge that doesn't have an edge? But that's to be defined. So here's an interesting concept of what I call popping out. So if you can see an object and you've observed it and you notice that it's red shifting, and you notice that it moved from red shifted to microwave shifted, and you know it's still continuing on, it's moving out further. So how would you observe it the next time? Well, we don't have the instruments to do that. So there'll be a gap between infrared and microwave where we just don't observe it. And then once it goes out further than microwave, we don't have the instruments to observe it at all. So it just continues on. Well, maybe if we created some instruments that would observe in longer and longer radio wavelengths, we could see that there's a lot of universe out there that we're just not observing at the moment. But we don't have any technology to do that. And officially, the international standards for radio frequency, no band goes lower than extremely low frequency, or ELF, which gets down to 3 hertz. Hertz is a cycle per second. It's a sinusoidal waveform. There are lower frequencies that do exist, and they've been measured in geophysical observations. So if you're measuring geophysical energy, I'm thinking earthquakes and such, very slow rumbles, they can sometimes take longer than 1 second for the sinusoidal wave to go peak to valley to peak. And they've actually measured one at 10 millionths of a hertz, 10 microhertz, which is a wavelength longer than the diameter of the Earth. So how did they measure it? Well, you just measure a peak and you wait for the next peak. Well, it took more than 1 year to measure a peak and then see the next peak and extrapolate the wavelength. We don't have any radio astronomy instruments that would measure a wave in its reality in real time end to end that long. You'd need very larger than Earth diameter receivers out in space, and that would be something that they've named the XLF, the extremely low frequency, but we don't have any astronomy instruments to observe that. But if you take that down to smaller and smaller fractions, you'll eventually get to near zero or 0 hertz cycles per second, which is not a wave. It's direct current, just a flat voltage. If something were observed and then it moved from visible to infrared to microwave to less than that, and we knew where it was in visual, knew where it was in medium infrared, and then lost it, it would just disappear in our observations until it finally stretched out and became microwave, and then we'd see it again. And if it was at the edge of the universe and stretching out further and accelerating and at a high enough velocity, we could lose it in microwave and then just not see it again. We don't have any instruments for that. So that would be popping out. Things that were there, then not there, then there again, then not there. And there's actually a research project to look at things that pop in and out. So in summary, as I say, the universe is vast and getting vaster or just expanding. There are discrepancies as to the actual value of the Hubble constant, and that the Hubble constant may be a constant now, but it might have been a different constant value in the early universe. And if you have a varying acceleration constant, that's known as a jerk. Name sounds odd because sometimes they'll call it a jolt just so they don't have to call it a jerk. Varying acceleration is known as jerk. And how do I know that? I work with small quadcopters, small little drones, and because the distance between their rotors is so small, their ability to change acceleration very quickly allows them to do flips. Like just push a button, they'll do a flip forward, flip backward, flip side, flip side. And the rate of change of acceleration in that term, that's the jerk. So that's where I know jerk from. At the moment, we believe the speed of light is a constant. Fingers crossed that it stays that way, because if we learned that in the early universe, the speed of light was not the same constant we know it as today, then some things will have to change. We can only observe things whose photons actually make it to our instruments. And we have a little assistance from something called Einstein rings. That's where gravitational fields get in between us and the object, and they bend the photons so they kind of concentrate them, and we can see things that would normally be too far away for us to see. But there are more distant things that are out there that the light hasn't reached us yet. Wait a little while, we can see more distant things. The Doppler shift continues on, so visible to infrared to medium infrared, and that's as far as we can take it. We don't have any far infrared. And then you wait a while and it becomes microwave, and we've got the ALMA and the Planck satellites cosmic microwave background. Our observations only go out as far as the longest wavelength supported by the instruments we create. But the objects continue to move outward, and they may be observed, pop out, be observed again, and then pop out, and then we run out of instruments to see them with. We can take the current size of the universe either by what we directly observe, but that's an extrapolation based upon spectroscopic shifting. And if we take that to how far it was and how fast it was moving at that time, and then we backpedal that to the co-moving distance, we can tell, well, how far out is it now based upon how far out we observed it, and we can sort of evaluate that based upon the light propagation time. But it makes the presumption that everything that we have seen is still out there. It didn't go so fast that it's suddenly all converted to energy at the speed of light, but we have no evidence of that. We're just assuming it's all still out there, continuing to accelerate outward, presumably with no exterior limit, and it's still up for debate whether the Hubble constant is an acceleration or a jerk. Lots of research going on here. Okay, question?
Yeah, if a Hubble constant is not a constant, it's not a constant. You can't call it that. Yeah.
I agree with that, but it's one of those things where if you know what the answer is going to be, if you can avoid asking the question, then you still have a good beat on things. But if you find out that the Hubble constant is actually not a constant, it's a variable measured as a jerk, then everything that you thought you knew about distances and movements in the early universe, you have to recalculate those. Because now instead of the Hubble constant being a constant throughout the lifespan of the universe, it's a curve. It's not a straight line. So yeah, the constant is not a constant. It's still a constant, but the constant is a jerk, not an acceleration.
You said that the Earth is not at the center of our galaxy and not at the center of the universe. Now by observation, we can tell it's not the center of our galaxy. Yep. How is it known that we're not at or near the center of the universe?
Because the center of our galaxy is not coincident with where the Earth is. So we're swinging around in an ellipse, and if every 250 million years, that would say the center of the universe changes every 250 million years. So yeah, we're not at the center of our solar system, we're not at the center of our galaxy, and we're not at the center of the universe, despite the cosmic microwave background polarization image showing the axis of evil.
Now, you said the universe is spherical. Is it symmetrical too, or could it be egg-shaped or pear-shaped? Or
well, within the approximations that we have, it's spherical. So in every direction we look, we can see out and extrapolate a co-moving distance that's the same in every direction. But if it's off by 1% in one direction versus another, then it wouldn't be spherical, it would be elliptical. And most of the things that have things orbiting them tend to be more elliptical than circular. And if they're more elliptical than circular, they're going to be elliptical spheroids. They're not going to be egg-shaped or spheres. There are spherical galaxies, but most of the galaxies are elliptical. There's also the concept that if something's spinning around a center point fast enough, then it becomes an oblate spheroid. In other words, it gets squished, but it's still out there. But if that were the case, then we should be able to look in a particular direction and see that the farthest things we can see are a different distance by some discernible difference. And we don't see that.
Look in different directions.
Well, that would only be if we could actually see to the edge.
No, because we can't see to the edge, but we can see the expansion that we can see. And based upon the Doppler shift of those objects, in every direction that we look, that distance for the same type of galaxies at the same color, Doppler shift are all the same. So we're presuming it to be spheroid. But that would also
say, I didn't quite understand what you said then about figuring out if the universe is an oblate spheroid.
Things that are spheres that are rotating fast enough become oblate spheroids.
Yes,
like
the Earth.
So far, we've not seen any of that oblate squishing in the universe, which would say, is the universe rotating? Well, if the universe were rotating, we would see an additional velocity vector in objects. And we haven't seen that yet, but the Rubin Space Telescope, after a full year's worth of observing, may have an additional vector that will tell us the universe is rotating, but we don't have that information yet.
How would we know if the whole universe is rotating?
If we're inside it.
Yeah.
How would we know? Yeah.
Because things are moving, and they move not in a single vector. They have multiple vectors, and you can have, what's the next level up? Tensors. you can have things called tensors, and a tensor is a matrix of vectors that give you, the 9 different directions things can move. To just say this is an object in space, and it could be moving 9 different directions all at once, different amounts in different directions. So we have these things called tensors, and when you look at an object in space, you can see that, oh, it's going that way. But if its wavelength is also shifting at the same time over your measurement periods, it's not only going that way, it's going out that way. So you can already measure multiple accelerations for an object. So multiple velocities, multiple directional vectors.
If we said that the universe is spinning, wouldn't it have to be spinning relative to something outside of it?
Yeah. What's the reference? Yeah.
No, it'd be like a galaxy. It would have to be spinning relative to something inside of it. And
so like if you stuck a stick into a fish tank and spun it, stirred it around a bunch.
Yes. And at the moment, we have no vectors indicating that the universe is rotating. If we did have a collection of vectors that told us the universe was rotating, we could find the center of the universe. By the summation of all those vectors would say where the central point of rotation is. But let's wait for the Rubin telescope to give us about a year's worth of data.
And so what do we think when we find out either way? I mean, one way or the other, what does that mean to us that we know this, we're the center of the universe, other than what, I guess we like to be the center of the universe, but other than that, what is the outcome of that?
The demonstration that they do that says we are not at the center of the universe, they could tell you where the center of the universe is if there's a rotational vector. If we discover no rotational vector, we still can't tell where the center of the universe is.
Do we need to know that? What are we going to apply it to?
Yeah, but if we know that, we got a better beat on things. We can put a little push pin on the corkboard that says, we now know that.
Oh, okay.
Knowledge for knowledge's sake.
It's not going to change the price of gasoline.
If the universe is indeed spinning,
yep,
wouldn't that play a role in the expansion of the universe?
That's a possibility because you have centrifugal and centripetal forces.
Yeah.
And
maybe that's
those could be the thing that's pulling stuff out.
Yeah, the cause.
Yeah. And then you have dark matter that's holding the galaxies together, if you believe in such stuff. We've got dark energy that's making things get farther apart. But within a galaxy itself, you've got dark matter that is holding things together as if it's one solid disk, as opposed to things moving around a center. Remember, they call them dark because we don't know what they are yet.
Yeah.
I wish they would have called them Fred and Ethel.
Or just unknown energy.
Oh, no. Research scientists don't like to just say, well, that part, that's unknown. Give me more billions and we'll go find it out. But they do have an approach, which is dark energy is not detectable. But we gave you $1 billion to go build research instruments to detect it. Yes, and we haven't found it yet, so give us another $1 billion.
Yeah.
There was actually that justification to a research project that had gone 10 years and not found any dark matter particles. And they said, we need the funding to continue the research. Maybe it's just an elusive particle, kind of like neutrino. But, I've always thought that dark matter is nothing more than photon wavelengths that we can't observe anymore. So if something starts out as a blue star, and then it goes through a wavelength shift and becomes visible, then red, then various bands of infrared, then microwave. Okay, there's a progression there. If the progression continues and the universe is as old and as big as it is, then what's the lower limit on that?
But that's not matter. That's radiation, right?
Yeah, it's something that can affect material by way of radiation pressure.
Oh, yeah.
So if you're looking for something to push on something, maybe it's all the photons that you can no longer see. It's like saying, I dropped my contact lens. Well, why are you looking at it a block away from you and dropped it? The light's better here. Why don't you go back and look and see what you need to see? Well, because then we might have an answer that says we don't have a good beat on things. And that's always uncomfortable for the scientific community. It's kind of like if you go back to when the Andromeda was the Great Andromeda Nebula in the late 1920s. I wasn't there for it, but I've got a textbook that says it. The Great Andromeda Nebula. I got that in a used bookstore. It was, I think, 1929 was the publishing date. But it was the Great Andromeda Nebula because they already knew from the images they had on glass plates that, hey, that looks a lot like the Milky Way. And then they started seeing other things that looked a lot like spiral galaxies. Wait a minute, maybe these things aren't nebulas. Maybe they're just like the Milky Way. There are other galaxies. Of course, now we're up to there's about 1 trillion other galaxies out there. Well, there was a period of time where there was contention as to whether other galaxies existed or not. We got over it. We learned to go, yeah, we got that wrong for a while. How long? Just a few hundred years. Well, we could find out other things in the not too distant future once the Rubin instrument starts giving us some data, and we could find out things like, hey, we found another vector, and the vector says the center of the universe is over there, and that it rotates, and therefore it's maybe not as flat, an oblate spheroid as the galaxies are. Maybe it's just a little bit squishy, until we make the observations and do the measurements, we don't know.
So what do you think, if anything, what do you think the universe is expanding into? Because for me, it's just unfathomable that it's expanding, but there's nothing that it's expanding into. Like, what's on the other side?
Okay. I've often wanted to do this experiment, but I just didn't get one of those round tuits. If I have a small container filled with tiny particles, and I put that inside of a larger container that is fully evacuated, and then the small container I pressurize beyond its breaking limit, and the particles go out. They won't go out in all directions because wherever my pressure source is, they won't be able to go that way, but they'll go out in a sort of a mushroom cap shape. What is the rate of acceleration of those particles in vacuum? Versus if I had air pressure in there and I still pumped it up to the point where it ruptured, what would be the rate of expansion of those particles? Well, in vacuum, it should be faster. But do the particles accelerate faster in vacuum? What is the rate of acceleration change in vacuum versus in air? Mm-hmm. It could be that if you have a high enough density of quarks that you'll rupture space-time to create new space-time that's literally a void that goes on forever, and the universe squirts itself out into nothingness at a speed that changes as the expansion stabilizes. So you start out with an acceleration that is faster, and then as the expansion starts to fill up space, there's less pressure between things, and therefore the expansion rate slows. And at some point, it'll be relatively constant. Not precisely, but it won't be a jerk. It'll just be a long duration acceleration. And I think that's what we're at right now, is a long duration acceleration.
Yeah.
What's it expanding into?
They're creating space.
But the infinite nothingness is also unfathomable to me.
That's the question, is it creating new space out at the edge? Or is there no edge and it's just pushing out into the void? Or as they said in the kids' movie, it's the nothing. It's expanding into the nothing.
They also said the void is the void. The void.
Yes. Don't be annoyed by the void. Okay. Any more comments or questions? Otherwise, I'll stop recording.